Shouldn't be super hard.
Just a measurement of force of gravity.
Force of gravity on an object, right? We can be more specific and say force of gravity is the force of generally the Earth so far until today, right? On an object, right? Okay. How do you measure it? How do you measure the weight of an object? Talk to your neighbors. How do you measure it? How do you measure the weight of an object? What's that?
On a scale.
On a scale. What's a scale?
That was a joke.
Oh, it was a joke? Oh, did anybody else agree? Do you think a scale is the right answer?
Yeah.
That's how I would measure weight. So, yeah, I mean, I'm sorry. Did you have a better answer? Do you not like that answer? I like that answer.
It's okay.
You measure the torque on the scale.
What's that?
You measure the torque that's acting on the scale. Yeah.
What is a scale? Let me ask that first. Is this a scale?
For sure.
Changing your answer. What is this?
It's a balance.
This is a balance.
What's the difference?
That's a good question. That's why we're here today. What's the difference between a balance and a scale?
One of them measures weight, the other measures mass.
High five for you.
Doesn't the scale just take into account, just multiplies your mass by your work?
If it's digital,
Okay.
right?
Yeah.
But not all scales are digital.
The scale measures just the force applied on it by whatever you set on it, whereas the balance, it has known masses, which if you were to put them on the moon or something, it would still have the same mass given by the balance, regardless of the lower gravitational force.
Does that make sense? Let me reiterate, say again, think this through out loud too. If I was headed to the moon and I had, 7 things to pack, I'd probably pack a triple beam balance as one of the things to put in my bag, right? I take this to and the frog, because you got to measure the mass of the frog. I measure the mass of the frog on the Earth. He measures whatever mass he measures. I take this whole system to the moon. Is my value going to change? Is my measurement going to change? No, because his mass doesn't change, right? Okay. I have a bathroom scale in the back, but I'm not going to go get it because you all have seen a bathroom scale, right? A little square you stand on. It's not one of those electronic ones that has little pretty red numbers. It's got a swing, you right, it spins. Okay. So I stand on that thing, or I put the frog on that thing, and it measures his what?
Weight.
His weight, his force, right? Now it's really actually secrets. It's really actually measuring the force that is being pushed up on him. Does that make sense? Okay? So it's kind of like, when I put the frog on the table, there's a force of the earth on the frog, and there's also a force of the table on the frog. Well, if I put a scale in there instead, then really what that scale is measuring is it's measuring the forces pushing up. Okay? It uses a little spring. Okay? That's why they often call them spring scales. Use a little spring that's calibrated for the earth. It's calibrated for here. If I take that spring scale to the moon, so some of them, I thought I used to have, I don't know where all my stuff is gone. But they used to have these at the grocery store. I don't know if they still do. Those scales that have the basket. Do you know what I'm talking about? That you put your fruit in, you put your oranges in there.
They still have this.
And they hang up like this. And then they tell you exactly how much your oranges.
Yeah.
They have those. You know what I'm talking about? Yeah? Okay. So really what's happening, this thing is all hanging, I put my oranges in here, and then it's pulling down. It's really just using Hooke's law. Right? It's really just pulling on a spring, and the amount that needle moves is based on how far that spring stretches. You guys with me there? Okay? If I take this whole setup to the moon with my 3 oranges, I hang it there on the moon, is it going to measure the same amount? No. Does that make sense? Because the moon isn't going to pull down as much as the Earth is. Okay? So the oranges are less expensive on the moon, right? Because they're not. I don't have as much, like, right? Unless you're buying them like each, and then I guess I don't know why you put them on here, right? So if if the oranges are whatever, so much per pound, better to buy them on the moon. I guess there's that whole like import tax issue, whatever, but that's whole economics. We don't care about that. But the actual cost, right, would be way, way cheaper on the moon if it was just based on weight. Is that making sense? Okay. So we're going to measure our weight using a scale. Let's write this down because this is important. You've known this for a long time, but it's not trivial, so we want to make sure we know. Okay? Mass does not change based on the force of gravity or the acceleration, okay? But weight does. Okay, that scale is going to change values, whereas my triple beam balance will not. Okay. So I got this little handout to give you. It's a little bit silly. I made it when I was a student teacher, and I thought that it was pretty good. I don't mind it. I still think it's valuable, so that's what we're going to spend a little time doing. So let's take a look at this. I guess maybe the color is even better, right? If you can actually see Bart in color. There he is. All right. So let's just look at what's going on here, and then I'll let you fill us out for a little bit, and then we'll talk. The game here is determining Bart's apparent weight. So Bart Simpson is going on a ride in a glass elevator, so we can see him. Yay, hi Bart, there he is. Okay, and he just happens to be standing on a bathroom scale. Because why not? Okay. If you ever have an opportunity to stand on a bathroom scale in an elevator, very interesting. Strongly recommend it. Carry that bathroom scale in your bag. It'll be really interesting. Okay. First task. We'll do one together. We're going to draw arrows indicating the size and direction of the forces acting on Bart. So we're going to do that first column together. He's standing still. No motion. Tell me. Acting on Bart. What forces are acting on him in this picture? Raise your hand if you can tell me one. Ooh, pick me. What? Gravity. Tell me what that is. That's the... Thank you. The force of the earth on Bart. Here we go. Where does that one go, by the way? Down. Straight down towards the center of the earth. So that's the force of the earth on Bart. Any other forces acting on Bart? There's a normal force. Now, he's not just standing on the floor, though. He's standing on something interesting. What's he standing on? Bathroom scale. So there's a force of the scale pushing up on him, right? Is that all right with everybody? Shouldn't be surprised. Determine the net force that Bart experiences in this one. What's his net force? 0. How do you know? I'm just going to keep that in mind. The strength of the Earth's gravitational field. What does that mean? I'll tell you. The Earth's gravitational field, that means, what's the acceleration due to gravity? So you can change that if you want. This really means, what's the acceleration due to gravity? What is the acceleration due to gravity in that first picture? 9.81, right? 9.8. And it says that Bart has a mass of 65 kilograms. If he has a mass of 65 kilograms, what will the scale read? Okay, so let's make it 10, shall we? That'll make our life easier. 10 meters per second squared. If you don't like that, you can get your calculator out. But the scale is going to read something about 650 what? Newtons. Okay? So far, so good? Okay. I'm going to have you work on the rest of these. For this bottom one, you can just tell me if it's greater than, less than, or equal to 650. Okay? Go. Have a conversation with your table mates. Work on this together. All right. Let me ask, my friends. How does... Are we okay to move on? Is that okay? I'm sorry. I didn't even ask. Or do you need another couple seconds? Couple seconds. I'm sorry. Let's give me a couple seconds. So, how does this free body diagram, waves moving at constant velocity, compare to this one? Same. How does this free body diagram compare to this one?
The larger force down. Or, sorry. Yeah, there's a larger force up.
Larger force up on this one?
Yeah.
Are there any extra forces?
Force of
Tension.
Oh, okay. Well, it's on him,
not
so
on
there's only
Thruster.
contact
A
force.
thruster.
What did you say?
They're not on Bart.
Not on Bart himself, right? So this one has scale and earth, this one has scale and earth, and this one's the same. I'm just going to write that down so we don't forget. So you're telling me this one's the same. This one is going to be the same except what?
Bigger force.
Bigger force going up. Okay, and I'll come back to the rest of those in just a second. So the force of the scale is just going to be bigger than the force of the earth. I just got ahead of myself. Let's go back to the constant velocity one. What's his net force in the second one? 0. What's the strength of the Earth's gravitational field? What's the scale read? Okay, you guys aren't like impressing me with your confidence here. Is everybody okay with this one before we move on? So then you have to start being loud. So everybody's good here. You ready to be loud now? So we agree on this, yeah? Talk to me about the acceleration. Oh, excuse me, the net force. My bad, net force.
Positive.
It's positive, it's going up, something like that. Yes, net force is up, net force is positive. You can notate that however you want. You're not going to turn this in. This is just for thinking purposes. Tell me about the strength of the gravitational field. Same. Okay. Tell me about the scale reading. It's going to be greater than 650 newtons. Did he gain weight? He like ate a bunch of donuts right as he was... No, he didn't, right? But he's accelerating upwards, and so apparently it appears as though he has increased his weight, even though his weight is exactly the same, his mass is exactly the same. You go through there? Yeah?
Less than.
Greater than
Oh, it
650?
has weight. Okay.
Yeah, sorry. Yeah. So the scale reads greater than 650. Tell me about this one. What's going on the next one? How does the free body diagram compare?
The same, but normal.
Yeah, so the scale is going to be pushing up less in this case, right? And the Earth pushes down more. But they're the same two forces. The net force in this case is which way? Down.
Can I give a complaint?
You can always give a complaint.
In your first and third free body diagrams, you didn't have the force coming out from Bart.
You are correct. I would agree.
Just
Good job. I would lose points on my AP exam. Thanks for catching that.
You're welcome.
Appreciate it. Sweet. All right. Tell me about the acceleration due to gravity in that one. Still same, right? Tell me about the scale reading. It's less than 650. So he loses weight. Loses weight, right? So I keep thinking that some year, right around New Year's, when all of those like weight loss commercials come out on TV, I'm gonna like some sort of buy some money and just be like, oh my gosh, right? If you just ride that elevator downward the whole time, right? While it's accelerating down, you lost weight. Like it's amazing, right? Not permanently, just you have to just keep accelerating downwards forever, and then you keep losing weight. That's good. We okay? His weight changes. He's close to, it's not like he's going to the moon, he's just on an elevator. And then I tried to trick you, apparently. That's the rumor that's going on over here. I didn't do anything. Tell me about the forces acting on Bart now. Just the Earth, right? Cole, this is just for you. I'm going to draw it really, really well. From the center of mass of Bart. Is that better?
That is better.
Okay. Thanks for
You
being
get
honest.
1 point on your...
Sweet! I got 1 out of 5! Yes! All right. Any other forces acting on Bart? No. Nothing else is touching him, right? And then we got the gravity. And there's none of those other crazy town forces. Net force acting on him? It's down. And in this case, I'm going to just say with certainty that it's equal to the gravitational force. Okay, I'm just adding that just like for our own purposes. Tell me about the acceleration due to gravity. Still 10. Tell me what the scale reads. Oh my gosh, it's like he doesn't exist. 0 newtons. Bart is what in this case? He is weightless. That's a thing, right? He is weightless. Literally, what does that mean? It means that if we try to measure his weight, it looks like it is 0. Okay? What? There's a very, very common misconception in the world, okay, if you talk to people, that if something is weightless, that means that there is no what acting? There's no gravity. A lot of people believe that if something is weightless, there is no gravity, and in fact, it's exactly the opposite. Gravity is the only thing acting. Gravity is acting on Bart. Gravity is also acting on the elevator and on the scale. Everything is falling at the same rate. And because it's falling at the same rate, it appears that he doesn't have any weight. Okay? Let me write that down really quick and then I'll answer your question. Is that okay? I just don't want to forget to write it down. So weightlessness really means that what? We're unable to measure the weight because anything that we would use to measure the weight, any scale, is also falling down at the same rate, okay?
Can't you just measure the inertial mass and multiply it by the acceleration of gravity?
Well, you could, sure, yeah. But you couldn't measure the gravitational mass in this case, could you? No, because he's not sitting still, he's accelerating, whee, right? Look at that, pulling that all together. Go ahead.
So, like, if he ended up getting the scale under him, like, on the elevator and stood on it, it would still be 0 because everything's moving together.
It would be. It would be. If you've ever been to one of those amusement park rides, they have the one that I can never remember the name at Adventureland that I love, right, where you sit there and it shoots you up in the air and then you sit, Space Shot, is that what it's called? Right, and then you're sitting there and you're like, oh, look, Des Moines is so pretty, Des Moines is so pretty. And they're like, oh my gosh, right, you know what I'm talking about? Because it drops. And just for a moment at the beginning, you know how your tushy just kind of like leaves the seat there just for a second? Okay, imagine you're sitting on a scale, right? So let's say instead of just sitting on the seat, you bring yourself a scale, bring that scale to Adventureland, put it on. They probably wouldn't allow that. They'd probably be like, no scales on the Space Shot. Too many physics teachers have tried this already, right? But imagine you're sitting on that scale. So while you're going up on the Space Shot, that's what I should do. Forget this elevator business. Space Shot, right? As you're going up on the Space Shot, you feel like you're, right? You're like being pushed way down. Doesn't it feel like you're being pushed down? Okay? That's really just this situation, right? So you gain a whole bunch of weight. You tell somebody that, like somebody who's like really concerned about their weight, they're like, oh my God, I would never ride that ride anymore. Ah! But really, it's just because weight is a very subjective thing, right? You with me there? Okay, so they gain a bunch of weight, and then you're sitting there again. You're just sitting there. Oh, you're not in the same weight. And then you're going to go straight down. You're going to be weightless. You are weightless. That's that weird like feeling you get in your stomach when you're falling at the acceleration of gravity, just briefly. And then it slows down a little bit, and then your butt hits the seat again, and then life is good. You know what I'm saying? But yeah, that's exactly what's going on. So even if his feet were underneath the scale, it would all still be measuring 0. Does that make sense?
Why
Go.
isn't it the same thing for the accelerating down? That's what I was going to say.
Here? No, here.
Yeah.
Because he's not accelerating down fast enough. So he's accelerating down, but if you're not accelerating down at 9.8 meters per second squared, there's still going to be a force up.
Well, isn't the scale accelerating down at the same rate? So
But the scale is feeling a force up from the floor. The scale is accelerating down at the same rate that Bart is, but the scale is so the way that a scale works, right, is that it feels a force from the floor up and from the person down. Are you with me there? And so if the floor up is still bigger than the person down, then it's going to measure something. Does that answer the question you're asking? And did you have the same question? You guys have like a mind meld thing going on? You just want to make sure the question got answered? Yeah.
For the last column, FG is just going to be 650.
650.
The same
Yes.
as-
No,
The same as the scale.
yes. Let me make sure I'm agreeing with that. The net force down is just, yes, mass times acceleration of gravity. Yeah. Does this make sense? Other things before we keep going.
So net force and free fall is the same as weight in, if you understand what's going.
In equilibrium. Yes. You could say that. I don't think I would take time committing that one to memory, but if that makes sense to you, then that's great. Is that okay?
Yeah.
Okay. Okay. All right. So this weightlessness thing is important. Okay. When astronauts are floating around, okay, you with me there? When they're floating around in their space station or they're floating around in their space shuttle, is gravity acting on them? Ask 9 out of 10 people that somewhere on the street, they'd say no. There's no gravity in space. I would say I really hope there is, otherwise we're not going to be going around the sun anymore. Okay, the gravity is what keeps us going around the sun, right? Okay, and then you think about the moon. Is the moon, what's the moon being held in circular motion by? The Earth's gravity. And if there's no gravity out at the moon, well, then we don't have a moon anymore. Are you with me there? Okay. Space shuttles orbit a whole heck of a lot closer than the moon, right? It's a big deal to go to the moon. It's a big deal to orbit the Earth, but we're not nearly that far away. So absolutely there is gravity. Yeah?
Well, this, like, the reason why we don't feel like the sun's gravity or any of that stuff, it all ties into the whole circular motion thing we just did with, like, just the inward force.
Yeah, you guys have heard of Isaac Newton before, yeah? Yeah, I'm gonna get us there. Is that cool? Okay. Isaac Newton, he's a smart guy. Not my favorite guy in the world, but and actually this is why I don't like him. Isaac Newton discovered. Wrong answer. Discovered means that it didn't exist before. Isaac Newton did not discover gravity, friends. That would imply that prior to Isaac Newton coming up with this theory, everyone was floating around. Woo! Isaac Newton's like, gravity! Right? Like, that did not happen. That doesn't make any sense. Isaac Newton did explain gravity in a way that no one had before. That I'll give him. The reason I don't like him is because he explained it to himself and then held on to that knowledge for it was something like 8 years or something like before publishing or talking to anybody about it. And he wrote to somebody, or there was some sort of thing about how he thought it was so exciting that he knew this and nobody else did. Like, what a jerk, right? Like, I know this, nobody else does. Like, that is I don't like that. That's not the only reason I dislike him, but that's, just one little taste of it. This is one of the things he thought about. So you guys know the story of Isaac Newton, right? And how gravity just came to him. What's the story? What was he doing? Something with apples, right? Making an apple pie or something. No, what was he doing? Sitting under an apple tree, right? So this is the story. It's not really true. But but it makes for a nice, like, you know, tale to tell children, right? So he's sitting there under the apple tree, and the apple falls and hits him on the head. Oh, gravity, I get it. That's not really what happened, but some people do attribute that idea. So the story that makes the most sense to me for a AP Physics 1 audience would be to say that he was sitting under an apple tree and he watched an apple fall, but while he did that, he was actually looking up at the sky and looked up at the moon. He was watching the moon. He thought it was so pretty. Okay, so he sees this apple fall. He knows because they've been dropping things for a long time before Newton. Okay, they've been dropping frogs for a long time before Newton. It wasn't like he was the first one who was like 9.8. No, that was like way before him. Okay, but he looked up at the moon and he said, oh, if the frog falls, the apple falls, does the moon fall also? Are you with me there? That was the big question that Newton asked. That was the question that no one had asked before, and that's what made him famous for this stuff. Okay? Because he asked a question that no one had asked, or at least really explored before. So this is a little picture. I'm going to try and illustrate it from his, like, big book on gravity. Here it comes. You're going to draw this too. There's the Earth. Okay? This is not a real photograph or anything like that, but it's a picture. There's the Earth, and I'm going to draw a mountain on the Earth. There's my mountain, not drawn to scale, right? This is drawn to make a point. Okay? And we're going to imagine somebody up on that mountain with some frogs, or maybe some cannonballs or something. I like frogs better, though. Okay? And so we're going to imagine what's going to happen if this person with this frog launcher starts to launch frogs. Okay? So at first, they're standing on the top of the mountain, you know, just kind of standing there. They throw the frog, projectile motion, yes? That's not a surprise to us. We've been doing that since, well, before my daughter was born, and that's been at least 6 months, so that's a long time. So there we go. So it goes like this, boom, and it hits the ground. Okay? So then we get a little bit better frog launcher. We're going to launch it a little bit more. It's going to go, yeah? Okay? All we're doing is giving it more horizontal velocity. That's all we're doing. So I'm going to, kick it up another notch. It's going to fall a little bit further and a little bit further. Yes, are we okay here? So in this case, all of these things are going to zoop, zoop, zoop. They're just going to keep falling. But I'm going to give it enough kick that same frog is going to keep going. And he's falling, isn't he? He's falling towards the center of the Earth. Come on, there it goes. But what happens? The Earth is not there anymore. Are you with me there? Okay? So he's falling, going at a constant speed tangentially, right? That X direction, if you will. But the ground just keeps falling out from underneath him. So what's going to happen to that frog? Where's he going to go? Yeah. And so that's when you have to make sure you're wearing a helmet, like a frog-safe helmet, so that when that frog comes back and hits you in the back of the head, okay, or maybe you duck, so it just keeps going around and around and around, that frog is just going to orbit the Earth. Are you with me there? Okay? That's all an orbit is. That's all it is. So an object in orbit, I can't spell. Try that again. Is just one that is falling with a tangential velocity high enough that it keeps missing the ground. Okay? Or the ground keeps falling out from underneath it, or something to that effect. That's all that an object in orbit is doing. Okay? So you know that the International Space Station is up there, right? Okay? And the International Space Station is up. I can't remember exactly what its altitude is, but it's high up, but it's not like anywhere close to like the moon's distance away. Okay? And it's just up there orbiting. So all it's doing, if we draw a little free body diagram of the space station, there it is. What forces are acting on the space station?
Gravity.
Gravity, the force of the Earth, right? Where does that pull? towards the center of the Earth. Okay? The force of the Earth on the space station. Any other forces acting? Any other forces acting? No. It's got some tangential velocity in that direction. If I just stopped the space station and then I let go, it's going to fall, right? Just like the frog. But because it's got some initial velocity in that direction, it's just going to go in a circle. Does that make sense?
So when they launch it, they have to launch it at precise.
They launch it at a higher velocity, and then they use rocket boosters to get it into the proper orbit with the proper velocity. But once it's got that velocity, it's just going to keep, yeah.
So if the,
Does that answer the question you're asking?
if the moon stopped, it would come to Earth.
Absolutely. Yeah. Do you have some sort of evil genius plan to like stop the moon? Or will you at least give me a heads up before you do that? So, astronauts on the space station, there they are. Whee, they're floating. Why do they float?
Because gravity's the only thing acting.
Because what?
Gravity's the only thing acting.
Because gravity's the only thing acting on them. And is it only acting on them?
Well, everything.
It's everything.
Yeah, it's acting on the space station itself, right? Yeah, so just as those people are falling, right, so you've got the little person inside here, if we zoom in, right, so here's our little person, they're falling, I'm falling too, but the space station is also falling, everything is falling, so just like Bart on here, okay, it appears that he can float around or she can float around. It's kind of cool.
Why don't they lose horizontal velocity?
Why would they?
Air resistance.
Is there air out there?
I think it's past this.
There is no air. It's past the atmosphere. Yep. So there is gravity. Absolutely, there is gravity. There is no air out there. Yeah. If you tried to do this, that's why this picture is not really realistic, right? Even at the top of the highest mountain on the Earth, okay, there's still air that would slow this thing down, so it wouldn't actually do that. But the idea is there.
What about like space junk?
What about it?
Isn't that kind of a problem now?
Sure, but what's your question?
Does it ever hit the space station?
Probably. I don't know. I mean, I don't know. I don't know enough about what exactly your question is to answer it.
Wouldn't that eventually just slow it down?
Well, there's probably ways to avoid actually impacting with it. I mean, I don't think that they're just like, just like blindly, like, whoa, right? Like I think that they try to avoid hitting things, or try to avoid having things hit them. Yeah. The other thing to remember is that most of the space junk that's out there isn't falling down; it's in orbit. So everything's in orbit, and because everything's in orbit, as long as you know where everything is at any given moment, then you can predict where it's all going to be. That's the kind of cool.
If you're is there like a very precise velocity that you go in orbit? What if you're going above that? You just still stay in orbit.
Why don't you hold on to that question for just a minute? Is that okay? Because we're going to get to something, and I want to make sure we get there that will kind of help to answer that. Okay. All right. So, what about all this stuff? So let's talk about what Isaac Newton did, what he thought about, how this all kind of fit together. Newton says, is the moon falling? And if it's falling, if the moon is falling, is the acceleration due to gravity constant? Because it's pretty constant on Earth, okay? We know now that the higher you go up on a mountain, it's going to change a little bit. But at Newton's time, we didn't know that. We thought, drop your frog, you drop your frog, you drop your frog, wherever you drop it, given the tools that we measure. I mean, like, honestly, if I gave Cole this frog and I gave him a stopwatch and I told him to go measure the acceleration due to gravity on the top of Mount Everest, and at the lowest point in Death Valley, he's going to get about the same every time, right? Because, sorry, your reaction time, I mean, it's good, but it's not that good. It's not that good. Even if you had a partner to help you out, right? Like, we didn't have a lot of technology at the time. So this is the way that Isaac Newton got through this. And what I want to do in the next little bit here is to actually walk you through his thought process. You are as smart as Isaac Newton. Ready? We're going to do it. Here it goes. First question. Question 1. to address to help figure out this answer right here is how far would the moon fall in one day? So I know that the frog falls a meter in a certain number of seconds. Okay? My question for you is, how far is the moon going to fall in one day? It would be the same as if the frog was falling in one day, right? How far is the frog going to fall in a day? Can you figure out that answer?
Because, like, the moon is sizably different size than anything on Earth.
Center mass. Center, it's not rotating, so all we care about is center mass, center mass. How far is it going to fall? That's what I want to know. Go. You can do this. This is not a hard question. These are kind of silly big questions to get us there, right? I'm not saying that this is like super practical question. Very far. How far does it fall?
864.
Wait. So what did you get for the time? So the time is 24 hours, right? Which is how many seconds?
60 square. Well,
86,400.
yeah.
86,400. Okay. 86,400 seconds. How far does it fall in that much time? It's a long way. What did we get? 4.2 times 10 to the
meters.
Do we agree with that? Yes or no?
Yes.
I don't think that's what I got. That's why I'm confused. 24 hours
No,
times.
I didn't score T.
You didn't square T? Okay, that's going to make a difference. Square T. That sounds better to me.
3.7
Times 10 to the what? That makes me happier. Yes. Does that sound, that okay with everybody? Is that matching what you got? Gotta square that time. Time squared matters. Okay. That's how far the moon would fall in 24 hours. If the moon is falling. The moon is falling. But I'm going to tell you that the distance between the moon and the Earth center to center, we were able to measure it a long time ago. By the time in Newton they knew this. That it was about, well, they knew it was about 4 times 10 to the 8th meters. So it would like hit us and go through and go past, right? So, moral of the story from that really quick calculation is this can't be right. This can't be 9.8. Are you with me there? Okay. So now we know how far it is going to fall. So that's the next question. Question number 2. Question number 2 is, how far does the moon fall? And the nice part about this is that if we can figure out how far the moon does fall, like geometrically, then we can figure out what the acceleration is. You with me there? If we know D and we know T, we can find A. So let's figure out, I'm gonna put this in here, in 24 hours. How are we going to figure that out?
Just goes around once.
Does it go around once in a day?
Yeah.
What's the period? Is the period of the moon 24 hours? What is the period of the moon? Does anybody know? So I'll tell you that the calendars used to be based on the lunar cycle, right? So So it's about a month. It's 28 days. It takes the moon 28 days to go around the Earth. Okay? So the period is 28 days. And to save you from having to do a bunch of other stuff, I'll tell you that that is 2.4 times 10 to the 6th seconds. But you're on the right track, Sam, about thinking about how to go about this. If this is the Earth, and this is the moon, and if that's the moon on day 1, day 2, it's going to be somewhere here. Does that make sense? It's going to have gone through some arc of that circle. We want to know how far the moon falls. If it wasn't falling, it would go in a straight line. Does that make sense? Okay, if we turn gravity off, okay, Brock has some sort of evil way to turn gravity off now and then. Is that true, Brock? Or have I exposed everything? Kind of. He's like, kind of. Haven't mastered it yet, but I'm working on it. Okay. If we turn gravity off, then, whoa, hi, what's going on there? There we go. Then the moon is going to go, and it's a straight line to there, because it's got this tangential velocity thing. Why? Like, what have I done to you? Nothing. Nothing. Is that better? There we go. Stop being goofy. Why? I don't know. I'm just going to do this on the board. It's got a velocity going like this, yes? Is that okay? Okay. I want to know how far it's going to fall here. Can you figure that out? Maybe? This is really just a projectile motion problem. Oh yeah, I love projectile motion. dx equals vxt, right? Figure out how far it's going to go in this direction. Okay? We can make ourselves a nice little triangle. Triangle looks like this. And like this. Whoa, I don't know why this thing hates me today. Come on, team. And like this. That's a nice right triangle. I know this distance. I told it to you a little bit ago. You can figure out this distance. Yeah? It's a right triangle, so you can figure out this distance, your blue distance. Yes? And then from that you can figure out this. Go. I believe in you. I'm going to write down those steps one more time just so you can remember what it was. Okay? This is the distance from the moon to the Earth. Okay? That had a value of 4 times 10 to the 8th meters. This is the distance in the x direction that we would go if there were no gravity acting. So that's going to be the velocity in the x direction times time. That time is going to be 24 hours. That velocity you can figure out because you're clever. Because you know how far it goes around in 28 days. And you know how long it takes to go around in 28 days. In 28 days, right? Okay. Find that blue part. Subtract off the distance it falls. Go, go, go. You can do this. I believe in you.